Hello, everyone. Thank you for joining today's webinar. My name is Caroline Hughes, and I'm here from the National Renewable Energy Lab. The Nice Future Initiative is an initiative of the Clean Energy Ministerial, and today's webinar will focus on the energy-water nexus. Can nuclear technologies build water security? Before we begin, I'm going to first go over a couple features of the webinar platform. You have two options to listen to the webinar today. You can either listen through your computer by selecting the mic and speakers radio button on the right-hand audio pane display. Or you could listen by telephone by selecting the telephone option on the right-hand display. A phone number and PIN will display. Panelists, please mute your audio device when not presenting. If you experience any technical difficulties, contact the GoToWebinar Help Desk at 1-888-259-3826. If you have questions, select the questions pane on your screen and type in your question. After the webinar is over, we will share this video to our website at nice-futures.org/webinars. Today we will begin with a welcome from Faith Smith and then hear from our expert panelists on their experiences in the nuclear industry and with water. We will then move on to a question and answer session. I would now like to hand it over to Faith for a welcome.
Thank you, Caroline. Hi, everyone. I'm Faith Martinez-Smith from ClearPath. We're an energy policy think tank based in Washington, D.C. Today's multi-country expert discussion about the energy-water nexus is a crucial one. The energy-water nexus is a vital global imperative for clean drinking water, which is fundamental for global health and has the potential to transform revenue streams for nuclear power given its multiple uses. Today's webinar is being brought to you by the Nuclear Innovation Clean Energy Future, or NICE Future initiative of the Clean Energy Ministerial, or CEM, which was launched at CEM 9 in spring 2018 in Copenhagen. The NICE Future initiative focused on flexible nuclear campaign launched a year later. The CEM is the leading global platform at the ministerial level to discuss clean energy deployment. Now with the NICE Future initiative, the initiative brings nuclear energy into global clean energy conversations. This week in Saudi Arabia, our NICE Future team has joined CEM planning meetings to tee up the next ministerial level discussions at CEM 11 on June 2nd through the 4th in Vina del Mar, Chile. As a supporting NGO partner of the NICE Future initiative that advocates clean energy solutions, we are delighted that the NICE Future initiative has engaged experts from over 60 countries in events such as these to discuss clean energy solutions. Contact the NICE Future team to find out how you can engage. I'd like to turn my time back over to Caroline Hughes, who will introduce our first speaker, which I'm sure will be an exciting discussion.
Our first speaker will be Diana Bauer from the U.S. Department of Energy.
Just give us a brief moment while we pull up the slides.
Okay, Diana, I'm now ready for you.
Okay, excellent. Thank you everyone for participating in this webinar. Today, John, Carmack, and I will tag team on behalf of the U.S. Department of Energy. First, I'll give a little bit of background on the Water Security Grand Challenge, which is a White House-initiated, DOE-led framework to pursue innovation for water security. And then John Carmack will give a little bit more detail on what we're doing under one of the goals that brings in nuclear energy. Next slide, please. So the Water Security Grand Challenge is basically what we've done is built on a history of over the last several years of developing our thinking as a department on the water security needs, the sort of energy-water nexus, and its importance to energy, and then also the opportunities to bring energy efficiency into the scene for energy, for water. The initiative started back in a couple of years ago. We started brainstorming on how to frame the initiative. We had a number of we had a roundtable that the secretary led a couple of years ago, and then we as a team within the Department of Energy came up with these goals on this slide. The goals address different dimensions of the energy water nexus. So first, launching desalination technologies that deliver cost-competitive clean water. So that is, that's a place where nuclear energy can certainly play. The second is transforming energy sector's produced water from a waste to a resource. Again, nuclear energy can certainly play a role there. Near zero water impact for new thermoelectric power plants, significantly lowering freshwater use intensity within the existing fleet. That also is an important, relevant to nuclear energy as well. Doubling resource recovery for municipal wastewater. That includes water reuse, energy recovery, and nutrient recovery. So, and then finally, small modular energy water systems for urban, rural, tribal, national security, and disaster response settings. That also is small modular nuclear can play a role there. So more information on the Water Security Grand Challenge is available at the website at the bottom of the slide. Okay, next slide. So under Goal 1, we've announced a prize competition on solar thermal desalination, and this prize competition hasn't yet been launched, but we expect it to be launched in about a month, so folks could prepare to compete in that time frame. So basically, the intent of this one is to accelerate technology innovation through design, development, and demonstration of desalination systems, and this is using solar power. And this one, we're trying to find niche applications, like, for example, in agriculture, or maybe certain types of industry where the solar desalination would be economically viable, and this prize competition will involve technology demonstration eventually, and will be, we expect it to be a multi-year, multi-stage competition. Next slide, please. Currently underway, also addressing Goal 1, is the Waves to Water Prize. This one is currently in stage 2, and this prize is addressing using wave power to convert to convert seawater to drinking water. So in some cases, you can, some of the designs are directly converting the mechanical energy from the waves to pressure to run RO processes. And again, this is aimed at probably remote areas that are obviously on the ocean. And you can see on the right that it's a 4-stage competition and ending with a demonstration. Next slide, please. So this prize is also currently underway. It is a resource recovery prize from water resource. So it's recovery of resources, including reuse of water, but then also recovery of energy and nutrients and other resources from municipal wastewater plants. And this prize is a ideation followed by more in-depth analysis of potential solutions. And for this prize, we're bringing together we're looking for teams that combine municipal wastewater plants and communities, academics, engineering consultants, et cetera. So a diverse team to develop solutions for these plants. Next slide, please. And now I'm going to hand it over to John, who will talk in more detail about Goal 5.
So good morning, everyone. Afternoon and evening, I guess. I think we have participants from all around the globe today. My name is John Carmack. I work with Diana on the Water Security Grand Challenge, and my responsibility is as the lead for the Goal 5, which is to deploy small modular energy water systems in cost-effective areas to serve areas where energy and or clean water is scarce, expensive, or challenging to obtain. You might think that water and energy are available easily across the United States, but that is not true. We have both energy and water scarcity issues across the United States, as is the case across the globe. And so for this goal, what we've tried to primarily focus on doing is identify technologies, advanced technologies that can provide us with better energy and water and pure and clean water in a variety of different areas, in a variety of different applications. The challenge concept that we've identified is to, really sort of euphemistically say, how can we provide energy and water in a box? Modular, easy to ship, easy to assemble, reliable, and providing energy water services at cost parity with some of the existing solutions. We've held a few workshops here in the United States with technical experts from around primarily the United States, and we've focused primarily on that so far to try to build something that's of interest to at least the US based technology providers. And in the Department of Energy, we've been trying to focus on how to establish a prize opportunity that is applicable to all energy supply capabilities, as well as applicable to a number of different and a variety of different water purification applications. So next slide, please.
Pardon us, we are having some technical difficulties. 1 second, please.
Well, if it's okay, I can continue to sort of talk while they're trying to get the slides back up and operational. In our activities for this goal, for goal 5, to develop small modular energy water systems that can be deployed by the 2030 timeframe, we tried to identify specific use cases that would be of interest, and we identified 3 use cases. They were primarily kind of associated with the scale of need and the scale of both energy supply as well as water purification quantity needs. In our first use case, we identified just a direct response and recovery to natural disasters and failure of infrastructure systems as a possible use. These types of response and recovery things are emergency sorts of deployments, say earthquakes or large storms that take out utilities, and at the large scale. But we need to bring something that can quickly be both shippable and deployable within a 2-day time period or 48 hours. This application would meet minimum requirements for water quality and production based on emergency action needs that we typically see today around the globe when responding to emergency situations. These systems would need to be reliable. They would have to be able to operate in difficult environments sometimes for up to possibly a year, off and on. And we'd have to have a competitive cost, because what happens in the initial response and recovery today is we basically send air shipments of generators, electrical generators that run off of gas or diesel, and then also water bottles. So there's a large distribution need for those kinds of systems, and to keep them going for longer periods of time becomes more and more difficult. We see there are potential applicable technologies that could fill this use case that span solar energy, wave energy, fossil fuel energy, nuclear energy, as well as wind and battery power. So we're looking for technologies that, again, are sort of easily deployable under this use case sort of scenario. In our second use case scenario, we sort of thought about the next scale up. So if you're thinking about that you've sort of solved the issues associated with being able to quickly deploy technologies that and capabilities to provide energy and water to communities, you might have to do that at a little bit larger scale and maybe at a longer sort of term reliability and time frame. So our second use case, we titled it Ensuring the Quality of Life and Resilience. This might be sort of responses to longer term and longer duration emergency situations where communities have lost their energy and water capabilities and utility systems for longer periods of time. So you may be looking at trying to provide energy and water to larger scale situations on a more on a longer duration time frame, such as if you've sort of gotten through the initial recovery process or response and recovery process, and now you're trying to restart communities, capabilities, and utilities. Maybe get some of the factories and job sort of driven workforce things back up and operational, or you're even trying to just simply provide energy and water to small communities that might be islanded or in remote locations. We think that this scale of technology might be a little bit bigger than the first use case, and so it might not have to be so transportable. You might be able to take more time to get this transported and into place, but they would have to have very low maintenance and still require not very much technical knowledge or training to operate it, and they would have to have a definitely better reliability over the long term. And then, so let me move to use case 3, which is the next slide, please. It's like the slides are back working now. And in this use case, we identified that there are urban and islanded communities that need integrated energy systems at a little bit larger scale. They have to be able to integrate with maybe new or existing grids. And so these systems have to be a little bit bigger and capable in terms of the size and operation. These systems, we think, would be multi-megawatt scale energy systems and capable of producing thousands of gallons of water per day, scalable, but yet on small footprints, and then locate them within existing infrastructure and integrate within existing infrastructure in developed communities. We think that all of the sort of traditional energy systems have applicability here, and it will depend on where these locations are, where the applications are, as to what kind of water purification system is used in conjunction with it. We think all 3 of these use cases have definite possibilities for some of the new and advanced nuclear technologies that are currently under development today around the globe. And so what we're actually trying to do, I think if you skip to the next slide or move to the next slide, that we would like to identify prize opportunities that cross across all of these use cases, and then sort of to develop a prize opportunity that breaks down the cost and barriers to having these types of technologies available to communities around the globe. So that brings me to sort of close out and the current status. The Waves to Water Prize that Diana referred to a few minutes ago is actually open, and it's open competition right now. There's a link to its website if you want more information on that. And then the Water Resource Recovery Prize is also open, and it's linked there today. The next steps for us across all of these goals is to launch the American-made Solar Desalination Prize competition, launch a request for information to better gather information on the thermoelectric goal. And then on goal 5 that I'm responsible for, we're currently trying to get an RFI or a request for information out to the community that we want to collect some more information on how we can best structure a prize opportunity that considers the modularity requirements as well as these 3 use cases, and what technologies are actually out there that could maybe help with all 3 or some portion of all 3 of these activities. And I think my last slide is maybe conclusion. Nope, joining the conversation. So we have links to continue monitoring what we're doing in these prizes and all of our activities in the nuclear energy space and from the Department of Energy. And here are the links to those social media outlets. I think that's the end of our presentation.
Okay. Thank you so much, Diana and John. I will now hand it over to Rakan Ayoub to talk about his experience.
Good morning. Sorry, I don't have a presentation, so you're gonna hear me speak. I'm Rakan. I work with the Jordan Atomic Energy Commission. I'm the Director of Project Development. Thank you for your presentations. I'm going to be giving you something more practical from what Jordan needs rather than what we have of technology. This is coming from America. I'm going to give you a little overview of Jordan, where we are right now, something on the nuclear program, and then we're going to start talking about water and what we can do with what we have right now from renewables, and hopefully in the future what we can integrate from new technologies and how we can work on bettering our situation in Jordan. Now, to start with, let's talk about Jordan for those who are not familiar. Jordan is a landlocked country. We have about 25 kilometers of sea line. It's about a $40 billion economy, $5,000, $6,000 capita, and basically we're mostly an arid desert, arid environment, except for the north. And as far as water is concerned, we got the number 3 poorest in the world. We're doing, we're going to be number 1 very soon. It's not good news. Now, as far as what we're doing in Jordan, as far as JAC is concerned, as far as JAC is concerned, we were established in 2007 and 8 with a law to actually start the nuclear strategy in Jordan because of to start the diversification of the energy resources. Now, for Jordan and producing electricity, we have several options. We have nuclear, we have natural gas, we have heavy fuel, we have local natural gas, LNG, oil, shale, renewables, and nuclear. Each of them has its pluses and minuses, but most of them are actually imported, and I mean imported regularly, and its interruption is catastrophic from a financial perspective on the budget on Jordan. Being a small economy means that when the price of energy goes up, it hurts your budget. Like we're talking about 2010, or 2013 or 2011, when there was interruption of the gas pipeline or gas from Egypt. The effect on the price of electricity was, we're talking about 3 or 4-fold, 18% of our budget was energy, and not good. So what we are doing in Jordan is actually finding a solution for nuclear. When we started off with large reactors. Due to the slowdown after the Arab Spring, right now we shifted to small modular reactors. What we have right now in Jordan from the last 4 or 5 years was also a shift to diversification, a successful one. Actually, it's considered a model in the region, which is the deployment of renewables, and it has worked well for Jordan. So this is where we are here, and we're talking. We have a problem with water. We need desalination was an option for Jordan for a long time, but because of the Jordan's dependence on imported energy and the fluctuation of prices, which has happened many times, desalination was not an option before. Now it might be a necessity. What we are working right now is putting together issues of how we can actually, now we have a big now we have, well, I think it was 1,000 or more megawatts of renewable coming online. We have the necessity to produce or to bring in desalination. We finished the project for water conveyor from deep aquifers, but we can't do much of that because there's not much more. So now we have to find an optimization of how we can actually find a way to depend ourselves on local energy, not something that does not put us in a position where we actually are subject to foreign risk fluctuations, supply or demand, and at the same time we actually have and meet the economics of projects. Now, renewable is quite cheap, but it's intermittent, and nuclear, hopefully SMRs are going to be and deliver what they are. We're working very hard right now to make sure we can deploy them. How are we going to put them together is the question of how synergy works together right now. This is where we are right now, and this is the topic of our studies, our research right now. A part of our work is water at JAC. Where we go from now is several options. We've before discussed. We on the table right now are several technologies for nuclear. We have pressure water reactors, and we have high temperature, which choose two different ways of which are optimal for two different ways of desalination. Now we know renewables, and we know there are ways now. There are technologies that are emerging to make use of for backup. Now we have to put those and see how we can couple them with SMRs. Now the fact of the matter is, SMRs and renewables are going to work together. Anybody who says otherwise is dreaming. It is now a matter of a couple of years. Renewables have only been very economic for 5, 6 years. So it's a new kid on the block. This is mature now. In the next 5 years, we will have everybody talking to everyone because it's a dire necessity. And this is where we are right now. And we'll see technologies coming in. What is the most optimal technology for Jordan? The water is 400 kilometers away from where the bulk of the users in Jordan are in the north. It's a small economy. The economics and the engineers have to work hard to find the optimal solution. And this is what we have right now. And this is where I'm sitting here with engineers, and hopefully you're going to give us some ideas. Thank you. Thank you very much.
Thank you so much. I'd now like to hand it over to AK Adak from India to talk about their experiences.
Yeah. Good morning. Thank you very much for giving me an opportunity by inviting me as a panelist on this webinar conducted by Clean Energy Ministerial Nice Initiative Future. I understand that today's theme of webinar is on energy, water nexus, can nuclear technologies build water security? To start with, all I can say that by this time, we all have come to know that nuclear energy plays a key role towards the supply of clean and green energy, not only as electricity, but also with the added value in terms of desalinated water and hydrogen. BARC India is having long-term experience on desalination and have a decade of experience and expertise on nuclear desalination. BARC is also associated with International Atomic Energy Agency in the field of nuclear desalination and plays an active advisory role. On today's presentation, I will present the role of nuclear energy for desalination and the activities and initiatives undertaken on nuclear desalination in our country, India. Shall we go to the next slide, please? Now, in my presentation, I will give the outlines of the desalination technologies and the advances on the desalination technology in present day. I'll come to the next one, the nuclear desalination. For this, the motivation for going to nuclear, Then the desalination plants, which are present day, which are being coupled with the nuclear power plants, how the coupling is being done. I'll also discuss on the some part of the design, development, and the safety aspects of nuclear desalination. Now, when we do the nuclear desalination, we need to do some thermodynamic optimization for coupling the system. Then I'll share my experiences of nuclear desalination, which is being carried out in India. And ultimately, we have set some goal for this desalination. Next slide, please. Yeah. Now to start with the desalination, and we understand all that there is a solution for this water scarcity. And we know the desalination is a process which can separate the salt from the salt water or saline water. It can produce various quantities and qualities of water, starting from industrial quality water, drinking water. Now to do this desalination, we need some energies which are either electrical or thermal energies of the present day desalination processes. This energy can be of various sources, either from nuclear power reactors or thermal power reactors, or maybe from renewable energy sources. Now desalination system can give a very good quality water, but at the same time it rejects a very high concentrated saline water. If it is a thermal desalination plant, it will have some temperature which will pollute the seawater environment, and again the concentrated water also will give some ecological imbalances towards the sea. So we have to see in a holistic manner that how we can do the total desalination with the objective, the optimization of energy as well as the total system of various considerations at a minimum water cost. Next slide, please. Now, present day technologies which are mostly used for this desalination, the well-established technologies are there. Those are called multi-stage flash desalination as well as membrane desalination. Now, the desalination technologies have shown their continuous progress with respect to their performances as well as material of construction as well as the efficiencies of their individual system. Now, for a thermal desalination system, the advances are there, that is called high gain output ratio, and for the compact system, in which case one should obtain the high heat transfer coefficient. At the same time, the overall construction cost should be minimized. So cheaper material of constructions are available nowadays. Sometimes an exotic material is used with respect to corrosion. In that case, the thin material is also used so that overall weight is reduced, so overall cost can be reduced. Coming to the membrane processes, for the seawater reverse osmosis case, the membranes are available with respect to high salt rejection efficiency. The membrane fluxes includes better membranes are available with respect to high chlorine tolerance. Membrane lives are extended, pre-treatment conditions are better, energy recovery devices are used, which can reduce the overall energy consumption. Next slide, please. Now, why we go for nuclear energy for desalination? The motivation we got that our main objective to reduce the overall energy consumption as well as the total cost of production. As you know, desalination is an energy intensive process. It needs steam or electricity. These are the two forms of energy which require the present day of a desalination system. There are other energies available like fossil fuel power reactors, renewable energy sources. But as we know that renewable energy sources are not stable energy sources. It has having some limitations which are intermittent in supply. And fossil fuels, reserves are limited. We should preserve them for our future use, like transport, petrochemical industries. There are issues with fossil fuel sources, as we know all, that greenhouse gases, which creates global warming and does not give a carbon-free electricity. Now, the fossil fuel, the energy costs are becoming higher and higher because of the adding various impacts of other costs, which are quantified in terms of human mortality, morbidity, global warming, and damages to ecosystem. So where we stand now? So we need a non-carbon clean energy system. Whether there exists a solution or not, let us see that nuclear energy can give this or not. Next slide, please. Now, nuclear desalination is an application of non-electric of nuclear energy application. Now, what is nuclear desalination? And when a desalination plant is using the power from a nuclear power reactor and producing fresh water from seawater. Why we go for nuclear desalination? As you say, that nuclear desalination can meet the challenges of increasing global demand for water and energy. And it can reduce the concern about the climate change and the volatile fossil fuel prices. Nuclear desalination can give the security of energy and water supply. Now, how to do it? With the use of steam and electricity. Now, there are thermal driven processes, there are membrane driven processes. The electricity driven membrane processes, which are generally cheaper than the thermal processes, but the membrane driven processes produces low quality of water, and of course it is very sensitive to the quality of feed water which is given to the system. Thermal desalination plants produces very high pure distilled water. It can be used for processed water, industrial water as well. Go to the next slide, please. Now, how to do this nuclear desalination for a heat-driven system? As you all know, nuclear power plant is having some concerns over radioactivity. Now, this can be avoided by giving a coupling barrier in such a way that radioactivity cannot go to the desalination plant side. And this, when desalination plant is using this energy in the form of steam, that there are some problems of activities, mainly let us say tritium, which is a beta active system, can be mixed with the desalinated water. So there are some ingenious features which are used here. Next slide, please. Now the candidates for this nuclear desalination thermal driven well-known multi-stage flash. The multi-stage flash desalination system, it needs steam at around 3 to 5 bar. Large capacity plants are exist which are very much economical and being used all over the world. It is having some scaling potential because it operates at a higher temperature at around 90 to 120 degrees centigrade. Here the steam economy is around 8 to 10 with higher number of stages. Electricity consumptions are around 3 to 4 kilowatt hour per meter cube. Nowadays, better technology, efficient technologies are available, which is a better version of multi-stage flash desalination, that is called multi-phase distillation, in which case low pressure steam at around 0.3 to 0.4 bar are being used. With the application of high pressure steam and adding one more equipment that is called TVC thermovapor compressor, it can give better steam economy. That means we can use the lesser amount of steam. MED system operates at low temperature, so scaling are less, corrosions are less. It needs very small amount of electrical energy, 3 kilowatt hour per meter cube of distillate. Next slide, please. Now these are the desalination system. We have to couple with the nuclear system. It's not difficult technically, but some considerations we have to think of, that how to avoid the cross-contamination with respect to radioactivity. Not only that, when the desalination plant is coupled with the nuclear reactor, sometimes nuclear reactor is not in operation, or sometimes the desalination plant is not operation. So sustainability sometimes is a problem. And other considerations like, the reactors are designed for a more number of years, but the desalination plant systems are not designed for those many years. So we have to think of in between new system to be designed, new desalination system to be incorporated in the system. So we have to see how to minimize the impact of thermal desalination systems with the nuclear reactor systems. Next slide, please. If we see the present day water-cooled nuclear reactors like PWR and PHWR, the thermal efficiencies are lower compared to fossil fuel plants. The efficiencies are around 30 to 35%. This is due to the fact that low steam temperature, pressure, and high moisture content. So about 2/3 of the thermal energy is discarded to the water body. And if this low level of heat is used gainfully for other applications such as desalination, it will improve the overall heat efficiency, thermodynamic efficiency, and by this process, we can save the fossil fuel and we can reduce the greenhouse emissions. And considering the amount of waste heat available in a nuclear power circuit in the form of steam, it handles more amount of steam per unit kilowatt hour electrical energy production. So that means in the circuit, more steam is available, more waste heat is available. So nuclear power plant can give a higher amount of desalination. Next slide, please. Now, worldwide experience of nuclear desalination, if you see, I will come back to the Indian cases. Japan is having several multi-stage flash MED plants coupled with their PWRs for their industrial use. Kazakhstan was having one MED plant and MSF plant coupled to fast breeder reactors, but present day it is not in operations. It was having a long experience on coupling of this desalination plant with the nuclear reactor. Pakistan presently is operating one MED desalination plant of capacity 4,800 meter cube per day desalination plant coupled to their Canop PHWR. China is also having some MED plants which are coupled to the nuclear heating reactors. Argentina has also planned the MED and of course hybrid RO plant to their PWR. Next slide, please. Now I'll come to the nuclear desalination activities in India, whatever we conduct at our department, in-house use. Sometimes we give the water to the public use also. We have various desalination systems, nuclear desalination system. We have some experiences on this that I'll share through this presentation. We have one nuclear desalination demonstration project at Kalpakkam. We have some experiences on waste heat utilization, nuclear desalination, utilizing the waste heat from a nuclear reactor. We have some plan on setting up desalination plant coupling with a nuclear reactor, which is called advanced heavy water reactor, which is a BWR, boiling water reactor, and SMR of 300 megawatt electric. We are engaged with IAEA activities on advisory role. We are giving the agency on the advice on non-nuclear, non-electric applications of nuclear energy. Next slide, please. Now, before going into detail of this desalination system, in what way what considerations we have given for the safety. See, safety is utmost importance when we talk about the desalination, because the desalinated water will be used not only for industrial but for the public. So the coupling system, the safety objectives should be ensured that no adverse effect on the safety of the nuclear plant, as well as no radioactive contaminations with the product water from the desalination plant. Now, the breach of multiple barriers should not be done at any point of time. So there should be multiple barriers. If one fails also, the second one will take care. So provisions for engineer safety features. There are various engineer safety features. One is called pressure reversals. Another is called, another heat, no contact heat driven system. Next slide, please. How we have done this nuclear desalination at our research reactor, Trombay, India. If you can see here, one desalination plant is coupled here, which is utilizing the waste heat of this nuclear reactor. This is the research reactor of 40 megawatt thermal. So all the heat is going to waste because it is not producing nuclear power, but the heat is going to sea as waste. You can see here one isolation heat exchanger is given here, which giving in turn the heat generated from this primary cooling water circuit is going to the desalination plant. This desalination plant is producing 30 meter cube per day desalinated water. This desalinated water is being used for the nuclear reactor makeup for this reactor. Next slide, please. We have done some simulation studies. We have operated the desalination plant at various nuclear stream temperature coming out from the reactor, starting from 77 degrees centigrade to 58 degrees centigrade. And we have seen that if hot water is available from the reactor at around 50 degrees centigrade, also that can be used for the desalination system and can produce a desalinated water. And subsequently, we are measuring the activities of radioactivities which is not breaching the barrier. So the isolation heat exchanger, these are the various points. We have kept some monitors, and the water is also being sent to laboratory at every 1 hour. So these are the studies we have given enough experience on nuclear desalination, particularly in smaller scale. Next slide, please. Coming to our Kalpakkam nuclear desalination plant, this is one hybrid nuclear desalination plant consisting of multi-stage flash plant and reverse osmosis plant. Multi-stage flash desalination plant is having capacity of 4.5 million liters per day, and our reverse osmosis plant is having 1.6 million liters per day. We have chosen this hybrid desalination with some objective that when the nuclear reactor is not in operation, at least RO plant can give desalinated water to the public. Now, this MSF plant gives a pure quality of water distillate. The part of this water goes back to reactors, and the remaining water with the post-treatment mixed with the reverse osmosis plant goes for drinking. Next slide, please. How we have achieved this nuclear desalination? You can see here one nuclear reactor, that is our called Madras Atomic Power Station. That is a 220 megawatt electrical power reactor. The steam is going to high pressure turbine. Then after that, it is going to the low pressure turbine. We have taken a branch of that, and that much of steam at around 4 to 5 bar is generating around 2.5 bar steam. You can see the barrier of heat exchanger is given here for production of non-nuclear steam, non-radioactive steam. So this condensate is returning back to the reactor. We have this hybrid system, the hot water coming out from this multi-stage desalination plant coolant system. That coolant water is going to the seawater reverse osmosis system. In that case, the flux of reverse osmosis plant increases. Of course, we'll get some deteriorated quality, but this overall product gives a WHO quality of water. This plant is operating since 2008, the hybrid system, and we have enough experience, around 12 years of experience, and so far we have not encountered any radioactivity in our water system. We are continuously measuring any activity related to alpha, beta, and tritium level in the intermediate circuits as well as the water circuits. So to gain experience on a demonstration, we carry out various experiments on this system. Go to next slide, please. We have some other experimental setup which are giving a simulated results of waste heat utilization from the various power plants. You know, in our country, we are having so many pressurized heavy water nuclear reactors, and as you know, nuclear reactors, the final condenser, the remaining heat goes back to the sea in the form of waste heat. So when, let us say when the temperature is available at feed temperature of 30 degrees centigrade, the waste heat coolant water is going at around 35 to 40 degrees centigrade. So lots of waste heat is available. So our department has developed some technologies which are based on thermal processes, low temperature flash system, which can utilize the waste heat of these nuclear reactors. Our country is having the plan of setting up 700 megawatt PHWR. So department has given the mandate that all the nuclear reactors will have the small desalination plants which will give the makeup water reactor for the reactor. Next slide, please. In the coming years, we are having a proposal of an advanced heavy water reactor, which is heavy water moderated, but a boiling water reactor. Here also we have planned for 2.4 MLD MED desalination plant. From the nuclear reactor, the primary heat transfer circuit, there is also around 5 megawatt waste heat is available. There also we have planned for MED desalination system, which presently is in the execution stage. Next slide, please. So this is the scheme how we are giving the multiple barriers, which is generating a non-nuclear, non-radioactive steam for the desalination system. You can see it here that the right side, the desalination plant, and there is a separation between the nuclear side and the desalination side. Next slide, please. Next, yes. So when we are doing this desalination, we do some activities on thermodynamic optimization, that how to extract steam at what point, which will give the maximum production with using the lowest energy. So we do some modeling work on this. We use the thermodynamic optimization program of IAEA, which gives the various sensitive analysis that how the heat extraction and power productions can be analyzed in a better in an Excel sheet manner, and ultimately we have to calculate the total penalty by doing this desalination. Nuclear reactor loses some power, so our objective should be the low power high desalination system. Next slide, please. We have analyzed various coupling system connecting with the nuclear reactor. With the one SMR, we have considered the AHWR, we say at capacity of SMR is 920 megawatt, 300 electrical energy. We have simulated various desalination system, SWRO, MED, combining the hybrid system, MED-TVC. MED-TVC means thermo vapor compression system. We have analyzed the system, and various coupling system have been shown at various cost figures, coupling with the reactor. Next slide, please. So this shows the various cost figures of desalination system coupled with the SMR. One is SWRO system, MED system, MED-TVC, and hybrid combining both the technologies. It shows that SWRO plant gives the lowest cost of water in terms of dollar per meter cube, around 2.64 for a capacity we have considered here of 3,000 meter cube per day. Of course, the cost can be reduced by considering the scaling up in future terms. And when the hybrid system comes, it has been shown that hybrid MED-SWRO plant will give both the qualities water for the industrial use as well as for drinking. Next slide, please. Now, by doing this, what are the challenges we face for this nuclear desalination if we are going for applying this nuclear desalination for the public utilities, utilizing nuclear power and producing desalinated water? The challenges are many. The location of the country, which is suffering from scarcity of water, but the nuclear power plant are not located there. So co-location is a problem. The location of nuclear power plant is so far that water transport cost is huge, so the total desalination system fails. So co-location is a requirement, at the same time minimizing the water cost. When the nuclear reactor is there, that means the financing, the cost, the nuclear liability, safeguards, security, everything to be considered. There are operational challenges, the two coupled systems of different lifetimes, and the management should see in a different directions for this cogeneration system. So economics plays a role, and of course the public perception, the socio-environmental aspects we have to see. Next slide, please. Now, nuclear desalination, when we are giving the water to public, the concern is that radioactivity, as I said earlier, and everybody will say that no, you don't put the desalination plant in my backward. So these are the fear we need to alleviate this thing. Another thing is that radioactive contamination. So definitely we have to give a confidence to public that product is radioactive free, and by scaling it up and number of desalination plants to be disseminated across the country so that the public fear will be there and it will not give any adverse impact to the countrymen. Even NGOs, sometimes they give a wrong direction towards this nuclear. Next slide, please. So coming to the conclusion of this thing, by setting up the nuclear desalination plants in our country at various locations, which have given the enormous confidence that nuclear desalination, not only it is technically feasible, but also feasible in terms of quality, quantity. And of course, the country needs the desalination and energy. So in that sense, the nuclear desalination will play a major role for not only energy security as also water security. So there are challenges are many for this desalination system, and whatever the knowledge we have got present day, we can say that nuclear desalination technology is well understood, it is feasible and can solve water scarcity issues. Next slide, please. So we have set a goal. The mandate is given to our by our department that go for a hybrid system which will give a sustainable production of energy in terms of electric power, hydrogen, as well as fresh water. So solar, there are two energy systems are being used. One is solar energy, another is nuclear energy. So by combining these two energies, we'll get three products. One is electric power, next is hydrogen, next is desalination. So flexible energy systems have been considered for our next goal. Thank you very much for your kind attention. Thank you.
Okay, thank you so much. We would now like to hand it over to Dr. Alodan to talk about his experience. Saudi Arabia.
Do I have a slide deck?
Oh, yes.
Well, hello everybody. I'd like to thank the organizers, and also I'd like to thank the panelists. I think a lot of information has been shared, especially from the last speaker, Mr. Adak. I really thank you for sharing such detailed information. I think we share some of the concerns that you mentioned. I'd like to go over a quick slide, which is a guideline for this presentation. We have a lot of information as a background. If anybody is interested, we can be offline and we can share some of these numbers. Basically, the presentation which tells the desalination status in Saudi Arabia, which is basically the strategic source of water in Saudi Arabia. Probably 70% of water comes from the seawater desalination. And also, what are the different things that we want to make this as a sustainable and long-term for next generations, which uses a minimum amount of energy and also environmental friendly. Next slide, please. So, as I said, the current condition or desalination profile in Saudi Arabia, and also some of the projects that we've used in renewable energy specifically. And I like to spend sometimes maybe 3-4 slides in what we call techno-economic assessment of nuclear desalination in comparison with other energy sources. As I mentioned in the previous speaker, that you can take steam from a thermal plant or a nuclear power plant, and that steam can be fed into MSF or MED and generate seawater by evaporation then condensation. I will come to that because that also will cost us on the energetics of the input. So if you go back, please, next slide. And the next, please, as well. So if you take the situation in Saudi Arabia, actually, next slide, please. The Saudi Arabia, probably we are the largest desalinator in the world. We have a capacity of about 8 million cubic meters per day. So if you look at for example, if you look at a 1 liter bottle, that becomes our amount of liters 8 billion liters per day. This is of course distributed among probably 32 to 35 different desalination plants along the Red Sea and the Gulf, the Arabian Gulf. The Red Sea is better for desalination because it has a relatively less TDS or dissolved salt than the Gulf. However, I believe the largest plant in the capacity is in the Gulf. It has 1.2 million cubic meters per day. And with these numbers, we are about 18% of the world capacity and 43% of the Gulf Corporation Council. And due to the expansion in population and economic growth in Saudi Arabia, we expect to increase this capacity by about 3.5 million cubic meters per day. So it's going to reach about 11 to 12 million cubic meters per day. Right now, the theme is that we have about 50% of the plant thermal and 50% reverse osmosis. The trend of increasing reverse osmosis because the thermal plants will use, of course, fuel. We use crude oil, heavy fuel oil. Some of the plants are diesel. As we go on and the government remove the subsidy in fuel, then thermal plants becomes more expensive. And at the same time, reverse osmosis plants operation and maintenance is getting much better than before. For example, the Gulf in the past, it used to be very difficult to maintain the membranes, but right now they can work with the hardship of the water salinity and high temperature from the Gulf. So reverse osmosis becomes much more easier to operate and with the less cost. So I believe the trend in Saudi Arabia will come to more reverse osmosis, and that will impact our study, as I will show in the slides that to come. Next slide, please. So as you know, desalination reverse osmosis has much lower energy than thermal, like MSF or MED, and it is about 1/4 of the requirement energy per cubic meter. This thermal desalination uses about 12 to 13 kilowatt hour per cubic meter, while reverse osmosis is about 3 to 4 kilowatt hour per cubic meter. So in Saudi Arabia, 20% of the total domestic energy consumption goes to desalination or water production. And as I mentioned, that the issue of this energy uses, if we take 8 million cubic meters per day and we translate it into energy requirement, that's about 60 gigawatts hour per day, which is a lot of energy that is used. And this is a strategic importance, as I said at the beginning. So we must look at how to minimize the requirement of energy and also the impact on the environment. So this is a serious issue that we're all working on. CARE is one part of many entities that work on this in Saudi Arabia. So if you go back, please to the next slide, where in the next slide we will, next also please, we will go to different projects that we used in the past. Some of them are working right now. We have in what is called Al Khafji, which is the top northeast of Saudi Arabia, and uses photovoltaic. And that photovoltaic is fed into reverse osmosis plant, which with about 60,000 cubic meters per day. The economics there are not very favorable and for the production of PV for many reasons, if we compare it to thermal plants. But it is a benchmark that we have set, and we believe that in future work we can beat that with about improve in the economics of about 50%. We have another project we have not completed yet, which is using CSP parabolic trough to generate steam, and that steam goes to an MED plant, existing MED plant. The MED plant receives steam from diesel boiler. We're removing that diesel boiler and replacing it with a field of CSP. We have the capacity of about 9,000 cubic meters per day to replace that. So we will have a solar utilization 50%. Next slide, please. The third project, which was announced recently from NEOM, which is a future city that is rebuilt in the west of Saudi Arabia, and it uses really an innovative solution where it basically draws the water from the sea, and whilst it's moving in the channel, which is covered with concentrated glass, it heats it up until it reaches a dome where the vapor is increasing the pressure, then the vapor condensed to a clean water or a desalinated water. So these are some of the three projects that we have already now in Saudi Arabia. And I like to go to the third part of my presentation where we discuss, or I show you some of the ideas that we're working on with the different partners. Next slide, please. So the goal is really to economically assess and compare nuclear desalination with other sources of energy. And these sources are CSP, natural gas and crude, and also coupling that source of energy to different power plants or different modes of desalination, such as MSF, MED, reverse osmosis. Then it's very important to compare hybrid system as well, MSF with RO or MED with RO. The reason for that, as mentioned by the previous speech, that when you take a pressure or you take a steam from, like, let's say, low pressure from a turbine or whatever spot you take that steam, you will jeopardize the efficiency of the whole plant to produce power. So we need to make that into consideration. We've done an exercise with SMR. We've taken a specific model of SMR, which is SMART. We are a partnership with the Koreans. And we check if we take some of that steam through MED, and if we take a complete power and we run reverse osmosis, we found that with a complete power system without taking any steam, actually it's economical. As I mentioned in the economics in the last speech, RO is the most economical technique that we utilize, and we believe that because it uses less energy, it has a better operation and maintenance than in the past. And if you take the fuel with international price, RO will be more economical. However, we need to make sure that the economics of both the electricity and the fuel are taken into consideration. Next slide, please. So these are some of the samples that we're working on energy resources, where we make steam, then from steam we make MSF, MED, then clean water. Or in the other side, in the bottom route, where we generate electricity, then reverse osmosis, then we do water. And I should mention that this energy sources, we're not just looking at typical what is available. For example, in nuclear, we're looking at BWRs and other technologies that mature in producing power, but also we are looking at a nuclear reactor that has been designed specifically for water desalination. As you know, the design of the power plant is very different power than nuclear desalination. Same thing with CSP. If you have CSP designed for power, it means that it has to be aperture of the parabolic, for example, opening is 6 meters, very high polished evacuated tube, so you can reach 450 degrees centigrade for the power. But if you design it for water desalination, you don't need that specs, so you can go to 110 degrees, which is enough for water desalination. So we're not looking at off existing design. We're also looking at a potential design that's dedicated for a nuclear, dedicated for desalination. And we believe that this is a very important to develop, because with that dedication, that's how you can be economics and really having this widespread all over the world. Next slide, please. So that's the previous one we showed is the single source of energy along with a single source of utilization. In this slide, you can do a many combination thereof of the source along with the utilization of different desalination plants. And as you see here, the combination of these will grow quickly. If you're not careful, you might go to hundreds of systems, which makes it more difficult to study. But we need to be very selective on the energy source and the utilization. We have about 40 systems that we're looking at right now with the economics and the designs. And we'll be more than happy to work anybody interested to share some of these data, and we have a better experience and benchmark with others. Next slide, please. So in the phase 2 of this conceptual design, It's really to provide feasible that CARE, which is the organization which stands for King Abdullah City for Atomic and Renewable Energy, with the Koreans research institutions. So we look at the dedicated design for the nuclear plant and also the different economics as we move forward. The design of the nuclear desalination plant will focus on improving economic efficiency and, of course, safety. Safety, a lot of discussion is putting a third loop, making sure that the radioactive material does not have any effect. But of course, that adds cost. So we're looking at always being cost or economics conscious, but also safety is a first priority, and also the environment. So it has to be all looked at the same time. And we believe that in order to have an impact on this high volume of millions of cubic meters per day, we believe that a nuclear will make an impact. However, is a nuclear going to feed the power to the grid? Then we take it to reverse osmosis plant or direct thermal. This is yet to come to be seen in an environment like the Middle East. And thank you.
Thank you so much. I would now like to hand it over to Jeffrey Preece, who will talk about his experience working with EPRI.
All right, thank you to our hosts and my fellow panelists. It's a pleasure to be with you. So I'm going to present two aspects related to our research in the areas of energy water nexus as it pertains to some specific nuclear energy focus topics. And my colleague Andrew Souter and I pulled together these slides, and Andrew works in our nuclear group, and I work in our generation side and also across the Institute through energy water nexus activities. So I'll first talk about where our research is focused on the advanced reactor technologies, and it shows where we think there are some potential opportunities for future connections within the energy water nexus. So in terms of defining an advanced reactor, a lot of folks are probably familiar and have seen the description of these technologies. I think what's important to highlight is we certainly see a space for all generations of reactor styles playing a part into the future, understanding that certain ones based on the remaining licensing or life of equipment will phase out, but then as other technologies phase in, that we see a clear opportunity. So number one, there's still benefits with today's commercial technologies, but number two, we see great potential for future advanced reactors, and it will maintain a critical aspect into these topics moving forward. So what you can see here in terms of the expanded mission and options around nuclear power, and a lot of our fellow panelists have discussed this already in great detail. So I'll just highlight a couple of key points that we agree with. Obviously, with the existing style and design, there's a clear opportunity around the thermal desalination aspect, so using steam generated by the reactor and also using waste heat in addition to supplement and improve efficiency. But then as we start to think about these Gen 4 reactors and the next generation technologies, it opens up a number of opportunities, specifically in this example showing where we see an optimal use for temperature and new steam production. And so from a water perspective, the high temperature steam electrolysis, it comes to mind, which is related to hydrogen. But when we think about where the hydrogen production could come from, obviously we're talking about water in the context of hydrolysis, and so or electrolysis. So where does that water come from? What do we do with the byproducts? Where do you co-locate these facilities? As mentioned by other panelists, there's a lot of impacts both socially and economically into some of these decisions that are being made. And so when we project out into the future and start to imagine this future with new nuclear, we see that the benefits and the opportunities exist for making nuclear a strong and to continue to be a strong backbone for a broader economy. And this economy can be based on electricity as it is today, but also expands beyond into, as others had pointed out, hydrogen, water, and potentially others as we think about transportation and other technologies which could be offshoots of, for example, the hydrogen economy. But then, as a number of speakers has pointed out in the topic of the overall panel discussion today, water availability is a critical component when considering any of these opportunities, both from a generation perspective, because we rely on a lot of water to facilitate the cooling and the operations at a nuclear facility. We anticipate that that could continue into the future with existing technologies, but with new technologies. And then also the dynamics that exist with needing water, clean water in places where you also need energy and electricity, and with changing profiles and operating conditions based on demand, having multiple options will become critical. But we have to also maintain that water will continue to be a critical resource need for the population worldwide moving forward. So our vision around advanced nuclear research is that these technologies are scalable, that they can be dispatchable, and that they achieve the zero carbon energy generation that that is being discussed and is being used to drive forward the future and the economies that we wish to achieve. We've taken big steps to incorporate this vision into our research portfolio. So those who are familiar with EPRI, you will start to see even more of these discussions come to the forefront as we anticipate what the future into 2030, into 2050 and beyond looks like from nuclear's perspective, and all of the changing missions and opportunities that come along with that. Our approach is twofold. It's both strategic and tactical. So in the strategic area, we're looking at the economics and the markets and realizing that there are key drivers which we have to be mindful of in pursuing research and technologies and innovation. And then on the tactical side, we're involved heavily in evaluating the technologies and helping to define what it means to identify, deploy, and establish these technologies as the technologies of the future. And that goes with risk, that goes with safety, that goes with economics, and all the things that comes with defining that future state. We've got a couple of results highlighted here below. I'd encourage you to visit our website. You can most easily type in the report number and begin to access some of the information. So now I'm going to switch into the portfolio of water, which certainly incorporates the opportunity for a future nuclear portfolio, along with other aspects. As been mentioned by my other fellow panelists, there's plenty of direct connections within the water energy nexus in terms of electric generation and the water needs. So we think about desalination, we think about water, municipal water makeup. And those direct connections could be steam. So we've heard a lot about thermal energy usage, electricity as being part of the grid or a direct connection to either desalination or water treatment. And then also the integrated technology combinations that come with siting, for example, desalination with power generation. So you have infrastructure like cooling, which plays a critical part. But another piece of the story is the reverse. And it's how we use the water systems to improve the resiliency and the reliability of the energy side. And so we think about things like demand response, where we use our water systems to balance the various missions and load profiles that come from the energy utilization component, so the electricity specifically, but it could also be the thermal energy, steam, and other infrastructure. We think about energy efficiency. So as many have mentioned, our demand and our needs for clean water are only increasing. And so it will be critical that the efficiency of these water systems, both desalination, water movement, and various uses beyond drinking water applications into agriculture and other industrial uses, that those technologies are efficient so that we can better maximize the energy and overall see reductions in greenhouse gas emissions, CO2 emissions, and other environmental constraints which might become more prevalent as we need to use more energy for clean water. The goal would be become more efficient in that energy utilization. And then also in terms of storage, we know that in big systems that there exists some capacity for storing energy in some way. And so we want to make sure that we have identified all of the flow paths that go not only from the energy supplier, be that the electricity or the thermal energy from the nuclear power plant to the water treatment facility, but that it is a two-way interaction and that those ways are both balanced. And now I'll speak just briefly about a couple of examples and how we've organized our research activities around the energy-water nexus. So we focused on, at a high level, technology innovation, where we're looking at new technologies and working with other researchers or companies to bring those ideas, bring those technologies into the commercial space. Looking at technology transfer, recognizing that there are water systems and energy systems being deployed in other applications, and how do we match those up for the benefit of all. Looking at modeling and analysis, because as was mentioned by the previous panelist, becomes very critical to understand the techno-economic components of very dynamic and very challenging systems and integrated systems. But then also thought leadership, and this is where we speak to pushing the boundaries, where we think about thinking beyond today's mindset. So how do we continue to explore and to push the boundaries into the future? So a few examples. In terms of technology innovation, we have a research portfolio that's dedicated to the water that's used to cool these systems, particularly in power generation. So we know that for thermoelectric power generation, water is a critical component to the process, and that there's a lot of water use in the power generation sector, primarily for cooling. And so we're looking at innovative ways that reduce that dependence of fresh water. That could be instead using air-cooled systems or hybrid systems. And then also looking at new technologies which allow us to store energy through the cooling concept and the cooling technology as well. In terms of technology transfer, I don't think I have to go into a lot of detail here because we've heard this from a couple of panelists. An example would be here in the US, where I sit, not far in Tampa Bay, Florida. You have a power plant that's integrated with desalination. Certainly, we've heard other panelists speak about this in the Middle East and in India and other places across the world. But what we find is that once you make these connections, the integrated components, the components that have to touch each other to enable that partnership, they become a source for potential concerns or opportunities, so that we can look at improving the efficiency of those connections as well. And so where do we find opportunities to gain measurable efficiency increases, both in terms of energy and water utilization, by combining these areas? An example in terms of modeling and analysis here, we're looking at the potential for using a water treatment system to respond dynamically to electricity demand. And so here we have an example of demand response at a 10 million gallon per day water treatment facility, where a baseline component shown by the top line represents the normal day-to-day, but then when we apply some demand response trends and analysis, we can see that we can save quite a bit of energy, electricity diverted to either another use or as a potential storage mechanism if you reverse the trends and look at it from a different way. So a lot of interesting things come up when we think about especially demand response, and we all know, are familiar with water systems preferring to operate at steady state. So what happens to the technologies when you have to deploy some type of load shift or changes, and what do the technologies do, how do they react, and then what cascades down into the full system from there. And then lastly, in terms of thought leadership, where in this case we're showing our economic evaluations for advanced reactors and designs. And this is where things get really complicated because it's not a direct analysis in many cases. So you can see here we have a number of examples where costs are relevant to not only the market, driving everything from the price of materials to the demand and the use of the end goal or the outcome of that facility, be it for hydrogen, be it for desalination or electricity. But also you have to incorporate the policy implications and what changes over a long 30, 50, 60 plus year life cycle with all of these changes. And then how do you model and account for all of the benefits and the value that comes from defining these integrated approaches? Because oftentimes we find that value is very hard to define, but that when we start down the path of bringing together all of the components of value for defining the future for advanced reactors and the different missions that they could support, that we gain a lot of momentum by aggregating these components, and sending a clear message is very critical to the future of where we see potential in advanced reactors and the integration with water for desalination, hydrogen production, and other missions which may exist. So with that, I'd like to turn it back over to our host. And again, thank you for the opportunity to speak.
Great, thank you so much. That wraps up the presentation portion of the webinar today. We would now like to move on to our question and answer session. So since we are a little short on time, we'll have time for one question, and then any questions that are not addressed during the webinar will be forwarded to panelists. So please send any of those follow-up questions to info@nice-future.org. So for our question, we would like to know from panelists what technologies are being considered to support limiting freshwater withdrawal for cooling.
So Carolyn, who did you want to answer that question?
Anyone can go ahead and jump in there.
I'll go ahead and take a shot. This is John Carmack.
Okay, thank you, John.
One of the goals that we had another set of slides that we had hoped to show this morning, but we didn't get them updated in time. Goal 2 of the Water Security Grand Challenge under the Department of Energy's effort is kind of targeted to what that question is addressing. We know nuclear power plants as thermal generating stations withdraw a lot of water for their secondary side cooling systems. And so the goal 2 of the Water Security Grand Challenge is to develop new and advanced technologies that could possibly do that. I know I'm not responsible for that particular goal in the Water Security Grand Challenge, but I know the kinds of technologies that they've been investigating and trying to incentivize are, improvements to efficiency of the water usage. So better materials, better systems on the secondary side that can more efficiently use the water, or even recycle it within their system. So I think, though not a great answer for the question, you can stay tuned to any announcements from Goal 2 of the DOE's Water Security Challenge for the kinds of technologies that DOE would be incentivizing.
Thanks so much, Sean. Jeffrey, we'd also like to know your thoughts on this.
Sure, absolutely. From our perspective, our research has been primarily focused on improving the thermal efficiency components and targeting some non-traditional methods to cooling. So as the example that I gave, looking at alternative materials that could serve as both the heat sink, but also as a potential energy storage device. We believe that there's a lot of potential left on the heat transfer mechanisms of the air side components. And as we've heard from a lot of colleagues who maybe are near a large body of water like an ocean, freshwater usage for cooling may not be an option. And so we've seen in other power generation applications the use of air-cooled systems or indirect cooled systems, but in very arid regions, the efficiency is not always beneficial or is quite low. And so looking for ways to either enable the use of air or indirect cooled systems that improve that efficiency through better materials or components, or also looking at ways to enable hybrid cooling systems where you're using at least some amount of water during a period of time, perhaps when you can improve the efficiency of the cooling process without requiring a lot of water for that application. So you could use a degraded water source and treat that to a sufficient quality for a short amount of time for usage, or you develop or deploy some type of hybrid model that runs at some continuous capacity and diverts some of your cooling need to various applications.
Okay, thank you so much. We would like to wrap up at this time. Thank you to all of our panelists so much for sharing your experiences and our attendees for tuning in. Again, our webinar slides and materials will be available at nice-future.org/webinars. Thank you very much, and we hope you have a great rest of your day.